Okay, good morning, everyone, and welcome to the Modern Machining Methods webinar series. My name is Dan Perry. I'm the Eastern Applications Manager for DP Technology, and today is part 3 of our Modern Machining Methods webinar series, Innovative Turning Techniques. So today's presentation will actually be broken up into 2 sections. Kevin Wismer, who's an applications engineer for DP and has been for about 4 years, is going to be our first presenter, and he's going to be talking about profit turning, grooving, and prime turning. Following Kevin, we'll have John Winter, who is a turning specialist with Sandvik Coromant, and he will be talking about parting and grooving. Throughout the presentation, we would encourage you to ask questions using the questions dialog in the GoToWebinar utility. And Freddie Wilson, who's been with Sandvik Coromant for about 20 years and is a machine tool solution specialist, will be answering questions live with myself throughout the presentation. So we would encourage you to do that. And then at the end of the presentation, we will do some live Q&A where we'll kind of cover some of the more commonly asked questions that have transpired throughout the presentation. So with that, I will go ahead and change the presenter to Kevin, and we'll get this thing started.
Thanks, Dan. As Dan said, my name is Kevin Wismer. I've been an applications engineer with DP Technology for 4 years now, and I'm going to discuss with you guys the advantages of profit turning and kind of the fundamentals behind it today. And so, as you can see on the screen here, profit turning is our high-speed roughing strategy, and these are some of the benefits that come from it. Reduced cycle time, increased tool life. And then the rounded transition moves are another added benefit. And so you see a lot of the similar benefits from profit milling are similar to profit turning here. All right, so what we have here is a traditional turning method. This is just using sort of parallel passes here along your z-axis. And some of the issues with a traditional turning pass like this, you have really high radial engagement on your entry moves, and there's sharp directional changes. These large engagement angles are really not great for your turning tools, and they create inconsistent chip loads. A lot of times when these passes are finished, there's uneven rest materials in different areas of the cut as well. And those large engagement angles can cause high and irregular cutting forces. And because of all this, you really have really poor chip control. And so these are some of the things that our profit turning cycle really helps with reducing or minimizing. All right, so here we have a look at our profit turning cycle, some toolpath here. And what we can see is one is just your profit turning pass, and that's similar to the traditional tool pass. You can define an engagement angle, which will actually control that engagement angle during that parallel pass there, which is nice. The second area that we can see here is the actual trochoidal motion. So we can control our trochoidal toolpath there, the size of those trochoidal moves. And that's when it starts to get into the areas where you would be more engaged in the traditional toolpath. Because of the trochoidal motion, we can really control that engagement angle, and we can keep a consistent chip load. The nice thing about it as well is you can have these roll-in moves, which help with the entry moves and exit moves. Again, just keeping that consistent engagement angle, a low engagement angle. The fourth area there is our smooth transitions. It's an option within the operation itself. So instead of having just very abrupt and sharp transition moves, you have much nicer, smooth, sort of what we call arcs there, instead of your typical bridge movement. It's a little bit easier on your machine. 5 is a trochoidal connection. And this is just how it moves in between the passes when it's using that trochoidal toolpath. And again, this is all controllable. The size of those trochoidal connections are controllable from within the actual operation. And lastly, the sixth area there is our corner picking. So in a traditional toolpath, when you're getting down to the small areas and like corners like that, that's where you get the really high engagement angles and where you're really burying the tool into some material there. Profit turning uses a corner picking strategy where it's just constantly going in and out of the cut and just keeping a small engagement using a trochoidal toolpath, and that helps with keeping a consistent chip load. Because of this, because we can control the small engagement angle and the consistent chip load, it allows us to really ramp up your feed rate, which is where you'll see that real reduction in cycle time, which is really nice. All right, so this is talking about the engagement control here, and this has to do a lot with the lead in and lead out, or the roll in and roll out. What this does is it eliminates the negative effects in a traditional plunging, and it's to maintain and reduce the consistent tool engagement. So the profit turning breaks the cutting surface into manageable pieces, and what we recommend is using round inserts to roll in and out of the cut to control that engagement at both tool entry and exit. With the smooth roll-in movements and using a smaller feed rate, the cutting force at the tool entry is really significantly reduced, and it's maintained at a consistent level. The feed rate is also maximized during the straight line movements. So once you're in the cut and you're not sort of entering in and you have that straight line movement, you can then ramp up that feed rate along those parallel moves. And while it's doing that, it's still maintaining a constant engagement, and then we'll reduce that engagement when we're exiting the cut. So that's how we kind of manage the engagement control there. And we'll see kind of options as to what we have there for within the operation. We're going to take a look at that. All right. So what happens when you have a part with small areas or sort of areas that aren't as smooth or easy to reach, such as what we're seeing here in this figure? Profit turning really provides great strategies for managing those small areas. The areas are often defined by these part profiles, and what we can use are our roll in and roll out arcs and that minimum trochoidal radius. By defining a minimum trochoidal radius, it's determined by the user in the operation, and what it does is we can limit that size of the trochoidal move in those small corners where a cutting tool can't really fit easily. And so what it does is you can basically have it define the smallest radius that you'll use, and then once it reaches that small radius, it sort of just leaves that material in those corners. So yeah. It's just the concept here is just trying to keep that constant tool engagement so that the roll and arc radius isn't too large here. All right, so we're going to take a look at this. In ESPRIT, the profit turning is going to be available in your solid turn roughing cycles, and then also the grooving cycle as well. And one thing I'd like to kind of stress here is that this is available in the newest releases of ESPRIT as well as older releases of ESPRIT. So whether you're on the newest release or if you're on, let's say, ESPRIT 2020, this is still available. There's no real difference between the two. So that's the really nice thing here. And I'll go ahead and pop over to ESPRIT. And so here I just have a part that we'll be able to illustrate these profit turning cycles on. And first we'll take a look at the roughing cycle and how we have that in ESPRIT. So here we go. So this is what you'll see once you're in ESPRIT and you're in the roughing operation. This is actually going to be the grooving cycle here on the left, and then the roughing cycles are going to be on the right here. Go ahead, over to ESPRIT. So first we'll take a look at the actual roughing cycle. So I'm going to go ahead and open up my roughing cycle here. And it's going to be on the rough page here. Once you're on the rough page for this cycle, what we can see here is right here are strategies. So you still have the traditional strategies here, your parallel to axis, offset, angle, and then you also have the profit turning strategies that correspond to those. So we have a profit turning with parallel passes, profit turning offset, and then profit turning angle. And again, you can switch between them, and you'll see some of the settings here change depending on the operation or the strategy you're using there. Okay, and profit turning. So here's where we can control the roll in and roll out radius in the operation. You can see we'll have an option to set as a percentage of the radius or the actual size of the radius. And I have this at parallel, and right here, we can see our profit turning section, and then here is the roll in, roll out radius. You can change that as needed. Next, we have the roll in, roll out feed rate. So when you are doing that roll in and roll out move, you can define the feed rate as a percentage of the defined feed rate in the operation. And so what I mean by this is, if I go back to the general page, this is the feed rate that I'm going to use throughout the parallel passes of the operation. But if I go to the rough page, I can define this roll in, roll out feed rate percentage as a percentage of that defined feed rate on the general page. So if I want to say maybe for the roll in and roll out, we want to reduce our feed rate to maybe 50% of that defined feed rate on the general page, I can do that right there. So here's where we can define the smooth transitions. Typically, you want to set alternate cut directions set to yes. That's what we always recommend. With these cycles, you typically want to use like a button insert or a full radius grooving tool, because when you have those tools, you can use both sides and you can do that alternate cut direction. And that's where you get a real advantage for reducing cycle time. And below that, you can see you can turn the smooth transitions on, which on that right image, you can see circled there. And that blue circle, those are the smooth transitions. So instead of doing your standard bridge movements, it's a lot easier on the machine to just do a smooth transition like you'll see there. And if I go to ESPRIT, you can see we have smooth transitions here and alternate cut direction. All right, next I'm going to talk about some tool selection for these cycles. So we typically recommend using a rounded, like a button insert or a full radius grooving insert. And this is because you can use both sides of that tool. So when using these round inserts, the entire cutting edge perimeter can be used for the cutting and the direction of the tool path can be alternated, and that will maximize the tool usage with higher efficiency. So that's where you're really going to get the reduction in tool wear and really increase your tool life. These round inserts also do a great job with your harder materials, your super alloys, Inconels. The profit turning cycle is actually designed for those hard materials. That's where a lot of the advantage comes in. You can still use it for, your softer materials as well. Standard tooling and standard traditional tool paths there's not too much of an advantage with the softer materials. But if you're having issues with like tool breakage with those softer materials, this is another great way to control chip breakage with the softer materials and controlling that engagement angle. So whether you're cutting soft materials or harder materials, the profit turning is really great for both. I do recommend using the insert we see on the right, where it's the button insert that has that center screw for fastening. It's a little bit more, it's rigid. The cutting forces when you're doing this, there is a potential when using like the larger insert here, if you're engaged in material and you do the upward pulling out while engaged in material, there's a potential that the insert, could pull out a little bit, but it should be fine with both. But we do recommend the center mounted or center fastened, screw fastened inserts. All right, so this is the part that we had kind of just looked at. We did run these tests on material, so we're going to take a look at a video here in a second. These are some of the metrics that we used for that video. And you can see here, 550 surface footage. It was on D2 tool steel. When using profit turning, we used a 50 thou inch per rev cutting depth of 40 thou, 42 degree engagement angle, and we typically saw a 22-second operation cycle time for that as compared to your traditional turning tool path, which is going to be a little bit longer. All right, so we're going to take a look at this video. All right, so what we can see here is profit turning on the left, and then your traditional tool path on the right. With the profit turning, you can see really good chip breakage. It's controlling that chip load and the tool engagement. On the left, we're already to the finish pass, and on the right, the traditional is still working down. So the profit turning is finished there at 27 seconds, and the traditional is just getting to the finish pass. And it's going to finish here at about 41 seconds. So you can see just on this one part here, there's a pretty large reduction in cycle time. And over a lot of parts, you can see where that return on investment can really come into play. All right, so I had talked briefly about these profit turning strategy options. This is just on the roughing page, and when you're selecting your strategy, you have these 3 strategies here. So you have offset, which actually will offset the actual profile that you're trying to cut while including the profit turning strategies. You have angle, which allows you to define a specific angle while doing the straight linear passes. And then you have parallel, which just runs those straight or parallel passes along the z-axis of your machine. So if I go into ESPRIT here, you can see here are the 3 options we had just talked about. If I go to the parallel section, you can define your step over or your depth of cut there. With the offset, we get, it reduces some of the settings that you'll need to set, but here's where we can define the minimum trochoidal radius, your maximum trochoidal width. And then here's the angle, the profit turning angle strategy. And what we can define here is an actual angle of the passes. So whatever angle you would want to cut at for those linear passes, you can define that there. What I'm going to just quickly take a look at is how the minimum trochoidal radius is going to affect the toolpath. So right now, if I set this to, let's say, a 10% minimum trochoidal radius and say OK. So this is where it's using those trochoidal radiuses. So we can see that there. I'm just going to go ahead and increase that a bit, and we can see how it affects the toolpath. So let's say maybe I want to use a 30% minimum trochoidal radius. And you can see how it allows for larger trochoidal radius here in the corner. So you can see that's how you can control how it's getting into those corners. If you wanted to use smaller trochoidal moves in those corners, you can reduce the size of your minimum trochoidal radius. All right, next I'm going to talk about some of the grooving strategies within ESPRIT. So we have single plunge, multiple plunge, zigzag plunge, turning, zigzag diagonal, which is like a ramping strategy. And then after that, you have your profit turning under the grooving strategy. These are all methods that Sandvik will go more into detail on from a tooling perspective in their presentation. Sandvik will discuss the most optimal programming methods for these cycles with your tooling considerations. Right now, I'm just going to cover the parameters available in ESPRIT for these strategies. And yeah. So single plunge move, that's going to be when you have a groove tool that sort of matches the groove size that you're trying to make, and it just does one single move down, and that's just the extent of that strategy. Multiple plunge move, that's when it's going to be a tool that you're going to need multiple plunges to create the groove, and you can control the step over that you're using. You can also define what's called a smart step over strategy, where it'll reduce the step over when needed to make sure that there's a consistent amount of material left on all sides of the groove. Next, we're going to have the 2 zigzag strategies. We recommend using a button insert or a full radius grooving insert because it's going to be going back and forth using an alternate cut direction. The difference between those two is that the first one is just going to do parallel passes, and then the second one uses sort of a ramping technique to move down. And I'll just go into ESPRIT here, and if I go into my grooving strategy, so here's profit turn grooving. So here you can see the different strategies. Single plunge, just as a single plunge. Multi-plunge, you can define your step over, and then the step over mode, the smart mode, will actually, you can either set it to constant or smart. Constant will always use that step over percentage. So if it doesn't really match consistently with the size of the groove, there may be a little bit extra material left on a certain side of the groove, whereas the smart mode here will reduce that step over when needed to keep a consistent amount of material on all sides of that groove. Pre-finish here, if you have an angled surface within your groove, with a traditional grooving strategy, there may be steps left there, and then you would come in and the finish pass would eliminate those steps, but that can cause inconsistencies in the finish pass because the amount of material there is causing inconsistent chip loads, where if we do a pre-finish here, it'll actually come in and clean up those steps before doing that finish pass. You can also define your plunge pattern here. So consecutive will just work its way across the groove in consecutive plunges. You can also alternate the plunges in a couple different ways. And if you wanted to do a peck groove, you can define a peck increment there as well. And then again, you have your zigzags and then profit turning. Profit turning gives you some of the same options or parameters as the roughing strategy. So we have the roll in, roll out radius, the feed rate percentage, your minimum coil radius. And that is profit turning with the grooving strategy and some of the grooving strategies offered within ESPRIT. So next we're going to talk about y-axis cutoff. This is we see this now, we're getting a lot of questions about y-axis cutoff. In ESPRIT, you can absolutely do a y-axis cutoff. The only way it's set up differently in ESPRIT is instead of your feature being along the x-axis, you actually just want to set up the feature along the y-axis or in the y direction. That's really the only difference for setting up your y-axis cutoff. There are some varying prerequisites depending on the machine type you're using. So if you're on a Mazak machine, you don't want to have any sort of X move in the operation. It's just a limitation for that machine for the y-axis cutoff. And then for Akumas, you want to make sure your work coordinate V vector is aligned with your tool path. But those are really the only limitations or prerequisites you need for that. And so I'll just go ahead and show you quickly the y-axis cutoff here. If I go back to ESPRIT. So what I have here is just a simple feature here, straight feature down the back face of the part here. Notice that it is parallel with that y-axis. If we're looking at the y-axis here, you can see that that feature is just parallel with it. I'm going to go ahead and just open a process. It's just a standard cutoff process. There's really nothing different about this process. It's just a cutoff operation. And I'll go ahead and simulate it real quickly. So what we can see here is there's my y-axis cutoff tool. What we should see when I simulate this is the tool will move along this y-axis. And so there is the y-axis cutoff. It's just as simple as that. It's just create your feature and just make sure that it's aligned with that y-axis. All right, the last topic I'm going to talk about today is going to be prime turning. This is something that Sandvik offers. And while we don't have a dedicated prime turning cycle in ESPRIT, you can do it. It does take a little bit more setup in terms of how you're going to change the feed rate, but looking at a programming time, a lot of times a little bit of extra programming time is going to be worth it because of the cycle time reduction that you'll see with the operation and also your tool life increase. So for prime turning, it uses a contouring cycle. The way it works is each pass for the cycle is going to have its own feature and its own operation. What we recommend is drawing out your roll-in profile and your roll-out profile if you're using a roll-out profile, and then feature them all. And then what you can do is put them all into a feature group. That way they're all kind of controlled, and it'll create that parent operation where if you want to change one, you can kind of click on the parent operation and change them all. And it uses, in order to change so the prime turning strategy here is that we're using a feed rate reduction in the entry move, and then you ramp that feed rate up. You ramp the feed rate up as you get to the more straight linear parts. And then if you're using a rollout move, you can then reduce that feed rate again. And I'm going to show you how to do that with an ESPRIT. It uses what's called insert technology to do that. So like I said, we're going to use one chain per pass. And then what we can do is set up a feature group. And then each chain will have its own operation. And that's going to define the entire prime turning cycle. And then this is what the insert technology looks like. So you'll set it up to insert, select the area at which you'd like to change the feed rate, and then go through and change your feed rates throughout the cut. Again, it takes a little bit more programming time, but it is advantageous to do this because the little bit of extra programming is going to result in a lot of reduced cycle time. And so what we'll do is we'll take a look at that right now. I'm going to go back to ESPRIT here. I have a different part here for this. So what you can see here, I have 4 passes that I'm going to do this on. Here's my feature group, each chain here. And then each chain represents a pass, and then each one has its own operation here. So once you have the operations set up, what we can do is go to the turning toolbar here. And in the turning toolbar, there's an insert technology function. You're going to use the insert section. And so my defined feed rate for the operation is 5 thou per rev. So we're starting off at a slower feed rate. So I would just select that portion of my toolpath. And then let's say I want to increase that as we're taking a little bit less of an engagement here. I'll put another one down here. So I select this area. And this time I can do maybe, let's say, 12 thou per rev. And then maybe once we get into this flat portion here, I'm going to bump this up to 28 thou per rev. Now I would want to do that on all of these passes, but that's how prime turning works there. And most of the posts will be set up for it. I have a post in here just to show you how that looks in the code. I'll go ahead and post this out. And what we can see here is my operation. So it starts out with a 5 thou feed rate. Then it jumps up to the 12 thou feed rate that I had defined. And then it increases once it gets to the flatter parallel section. So there's your 28 thou feed rate. And then I also had added previously the reduction in feed rate towards the end of the operation. So towards the end, when we're rolling out, you want to reduce that feed rate. And I already have the insert technology added there. And you can see then it reduces to back down to that 12 thou reduction, or 12 thou per rev reduction, and then 5 thou. And so yeah, that's how prime turning is set up, and it is a really good tool to use within ESPRIT. So that's what I have for my presentation, and I'm going to go ahead and pass it over to John Winters, who's going to talk to you about some of the tooling considerations for these cycles.
Thanks, Kevin. That was great. Let's see here.
So you should be getting control now, John.
Yep. So we're going to continue talking about different groove types, part off and y-axis. So as you can see here in this illustration, Sandvik Coromant has quite a few grooving options, both internally and externally. As Kevin had stated, there's different ways to do this. There's a single cut groove. There's the multiple, where you're going to use the smart or in the step over, or possibly do the alternating plunge. There's plunge turning and then ramping. One thing that we need to make clear is Sandvik Coromant has several geometries that are available for either cutoff, which is what the C is for. So cutoff for finishing medium. We actually have a G for grooving, which is more of a plunging type grooving operation. The T is actually, we can do plunging and side turning with these tools, and then the R would be full radius, and then the A is designated for aluminum profiling. So when you're roughing out a groove, the simplest and easiest way is just to do a simple step over. The thing is with a simple step over is it's not necessarily a balanced cut. Now in ESPRIT, you can actually give the amount of the step over so you can utilize as much of the insert as possible, but you're still using more of the face and one radius of that insert. So it's not as balanced and you tend to lose chip control. The preferred way if you're doing some sort of plunging is to do an alternating. This allows you to capture the insert or the chip, which allows for better chip control, and it allows you to use the full width and both radiuses of the insert. So you can see here, positions 1, 2, and 3, you're going to be completely engaged in the material. It's a full width groove. And then positions 4 and 5, you will not use a corner radius. You need to use about 75 to 80% of the width, and you need to make sure that you're centered on top of that for best possible chip control. This will give you good even tool life and chip control. So you can see here the recommended method is going to be the alternating on the top. We capture the tool, we can get better chip control because when you capture that insert, you're engaging the chip breaker that's designed on the insert. Whereas the lower one, the minute you step over, that chip tends to fall towards the area where you've already cut the material, which allows the chip to string out, and you can have poor chip control and an unbalanced cut, which is actually going to apply some pressure on the tool and possibly some deflection. For deeper grooves, we can actually alternate where you take a shallower groove, clean the material out, and then actually step down deeper and alternate your way in. This just helps with the chip evacuation so that you're not going too deep and binding up chips into the slot. Now, Kevin had talked about the plunge turning, and here's an illustration of a plunge turn and then also plunge ramping. So you can do a plunge turn where we can utilize the side of the tool using the T geometries, which is for turning, so that you can actually plunge in and then actually feed radially across. And the depth of cut when you're using these tools should not exceed 75% of the width of the insert for your depth of cut when you're side turning. So there is some methods to this because when you plunge in and start to side turn, if you don't back off a thou to 4 thou, you can risk chipping out the insert because you bind that insert. Because the minute you side load it, it wants to flex, and it needs to flex because you're going to put some clearance on the back side of that insert so it's not rubbing. So it's good practice to retract slightly before you start doing some side turning, and then when you alternate and plunge in on the other side, you will continue that type of method back and forth as you take the material out. And it's the same method as if you're ramping, except we're going to come straight across and clean the material out so that we're never any deeper than that 75% of the width of the insert. Here, as you're roughing, your best practices is to step down away from the shoulder and then come back and clean that up at a later date with a finishing pass. And then when you actually finish the groove, it's good practice to actually create a little bit of clearance down at the bottom. Again, this gives the insert room to flex and give some clearance so that you're not binding it and possibly chipping out the corners of the insert. And this should give you the best finish possible and reduce any risk of vibration. Now, profit turning. And we saw in ESPRIT, profit turning is extremely flexible because you can control your arc and radius either by the radius of the tool or by the percentage that you put in. And it's very important that you make sure that you use those, and you want a light engagement when you're doing the profit turning. This allows for a thinner chip where you can actually have higher feed rates and utilize the speed of the machine to get the material out. And we clearly saw that in the video that Kevin had shown versus a ramping. This is a good illustration of what we're talking about. As you roll through that corner, you increase the engagement of that radius on the insert. And the more engagement, the bigger the risk for vibration and chatter. So you want to try to keep that as big as possible. And you can see there the program radius is 50% of the IC as we roll through. So the depth of cut is 25% of that radius. And that allows us to roll through for better chip control and uniformity. And then with that thinner chip, we're able to take advantage of the feed rates and have reduced cycle times. So that's kind of the grooving aspect. We'll talk a little bit about part off. And the biggest thing about part off, it's like grooving, except if you're doing a full bar, you're going all the way to center, and you really do risk binding up chips in that groove. And that's why the modern geometries actually buckle the chip, and it creates what we call a watch spring. And a watch spring chip is not a bad chip when you're parting off, because the chip is narrowed, so it's buckled, and it winds up and it actually ejects out of the slot fairly clean. One thing that we need to be aware of as we're parting off, that as you get towards that center of the part, you maximize your surface footage because your RPM of the machine is limited. So you need to be aware of that. So as you come into there, you want to make sure that you reduce your feed rate. This helps reduce the tendency for vibration and too much tool pressure. And then the other thing you may want to look at also is as you get in towards that center, because your surface footage is getting to zero and you're actually losing heat, you want to turn the coolant off, because if the insert's too cool, you risk having built up edge and causing premature wear on the insert. The other thing you need to be concerned about when parting off is your centerline height. If you are actually too high above center, your clearance will decrease and you'll put a lot of pressure on the front of the insert, which will cause rubbing and excessive flank wear, which could cause breakage and premature wearing of the insert out. If it's too low, you'll actually leave a bigger pip, and here the cutting forces actually want to take the insert and rip that front edge off. So again, you're going to wear the insert out prematurely. The other thing you can look at is a handed insert when you're parting off. And this is good if you have a pick-off operation and you know you're going to be doing facing on the secondary, on the sub spindle. You can leave the pip on that part of the material and face that off. If you have a drilling operation that's coming in, you may want to leave the pip on the bar side so that it doesn't affect the drilling operation on the sub. So you can pick your hand a tool and put the pip on one side or the other, or you can continue to use a neutral tool, and that'll leave a little bit of a pip on each side. Another thing that you need to be aware of if you're parting off into a drilled hole is to make sure that you're parting off clean, like you're parting into a tube. It allows for better exit, more consistency, and because you can actually change the cutting forces and the direction and cause some issues with flexing of the blade, which could cause some issues. So you want to make sure that you're parting off into the round part, not into the angled surface of the drilled hole. So again, here's kind of an illustration. If you're using a handed tool, you do change the cutting forces. So it's recommended that until that insert's completely engaged into the groove, you should reduce your feed rate slightly and then pick that up once the insert's fully engaged. Helps keep it more stable in the cut. And then depending on which hand, again, you're going to put the pip on one side or the other. And then typically with a neutral, the pip will fall off. But you can see the cutting forces. So if you're doing a fairly big diameter and your blade's hanging out quite a ways, you may want to look at using a neutral versus a handed, because you will get some deflection. So a quick little review on the parting off is reduce your feed rate by 75% or for the last 80 thou prior to the part falling off. You want to turn the coolant off to reduce the risk of built-up edge, especially in more gummy materials. You want to make sure your center height is correct. Again, if you're above or below more than 4 thou, you're going to cause some issues in premature wear and possible breakage. You also want to keep that blade as short as possible for the best rigidity possible. And then if you are actually using a sub where you can pick it off, let the sub do the work and actually change the RPM between the main and the sub slightly to help break that pip, and then retract that sub. You can move off the face of the part and then retract and go to the next tool. Just gives you a better tool life. A lot of times if a part falls off, you can bind and insert and cause some chipping also. Now Kevin showed the y-axis. which is a new method for parting off, helps increase the rigidity and productivity. So traditionally, when you're parting off with a standard blade, you put a lot of forces on the edge of the insert and across that blade. And so you can see in this illustration here, you're creating a lot of undue pressure. Whereas if you use a y-axis, it's the same cutting action, except now you're taking all those forces across the strongest part of that blade, which gives you a higher rigidity with that blade. So in this illustration here, you can see the rigidity increase is over 600% improvement in rigidity just by changing the position of the blade. Now, changing that position of the blade gives us multiple things. It gives us more rigidity, which means now we can actually do larger bar and have that sticking out farther. Reduces vibration. We can actually pick up the feed rate, and we can actually have a better quality part off when we do this. So this can be used in a multitask machine, as illustrated here. So it's just a matter of putting it into the main spindle and positioning it so you can use the y-axis. So again, all those forces go through the blade into the turret. And you can see in this illustration the size of the bar we're able to achieve because of the rigidity of that. You can also put it into a traditional lathe. Now this platform will use the same tooling block and the same insert. All we're really doing is changing the blade. One thing you need to note is when you're actually putting these tools in the machine, it is very important that you follow the setup. On the blade, they're laser marked on how to touch it off and what offsets you need to put in, because the positioning of the insert is not where you would think it would be. So there's two different offsets depending on the blade that you're using, you need to put in when you're applying these tools. So again, here it's the same tool holder, just a different blade and the same insert. And you can see the top of the y-axis blade that's in the tool block actually has a flat on the top. So that is one area that you will touch off using your probe. And then you'll actually touch off the front of the insert. And then the offsets are laser marked onto the holder so you can actually put in the correct offsets for that blade. All the QD blades have coolant through, both over and under, for better performance, better tool life, and better chip evacuation. Not only the y-axis, but our standard blades also have both over and under coolant. And again, it's just the blade that changes, and this is just an illustration. There's 3 blades that we sell that you can put into our standard holders and use the QD inserts and go to y-axis. With that, Kevin, I'm going to turn it back over. I know mine was pretty short and sweet. You did a great job covering all the different types of grooving, so it's all yours. And I'll take a look at some of the questions.
Thanks, John. All right. So I think now we'll move into the Q&A portion of the presentation. Dan, I think you were maybe taking a look at some of the questions.
Yep, I've been answering them throughout the presentation. One thing that came up quite frequently is people are asking where they can view the webinars afterwards, and they're located on our website. If you go to ESPRITCAM.com/webinars, you can see the recordings of all of our previous webinars, as well as register for our upcoming ones. So we have another one scheduled next week that you might want to check out with a couple of our other partners. So going through some of the other questions, actually there's one that I would like to get the opinion of one of the Sandvik experts. I'll tell you, what my answer was first, and then we'll see if you have something to add. But one of the attendees was saying that they have a hard time convincing people about prime turning because the machinists are in doubt when they're pulling, cutting away from the chuck. So it makes them uneasy in comparison to a conventional cycle where you're cutting towards the chuck. And my answer was that the cutting forces are greatly minimized with the light radial engagement, which results in little to no spindle load. But you always have the option to cut, like with the profit turning operation, you have the option to set alternate passes to no, which would allow you to only be cutting into the chuck. But as far as prime turning is concerned, I don't know if you guys have any suggestions or things to consider there.
Well, when it comes to prime turning, in the high feed direction, which is typically when you look at a way a part is set into, say you're doing a shaft, and typically when you're looking at a shaft and a lathe, it's always turning towards the chuck with the larger diameter on the chuck side. So with the high feed direction, you would be turning away from the chuck to rough, but you can still use the front of the tool, which would have either like an 80-degree nose or like a DNMG type nose if you're profiling, to traditionally turn and finish the part. Yeah, there's a lot of concerns when it comes to pulling the part out. I have not moved a part yet, but you need to make sure, like if you're doing a part where you're grabbing a 3-inch diameter and you're only holding a 1/4 inch and you have nothing on the backside holding it, yeah, then there would be concerns. But if you're grabbing a part and it's a solid grip, and if it's a long part, you're using a tailstock, I've never had any issues with, I've had more issues with, I've stalled the machine with prime turning, but I have never moved a part with prime turning. Hopefully that answers the question.
Yeah, I think that was a good answer. So let's see, one of the other questions was, on a full radius grooving insert, do you need 2 offsets, one for each side of the tool? And the answer is, it's really up to you and what you're trying to accomplish. In my experience, with this being a roughing cycle, you wouldn't necessarily want to use cutter comp. That would be more for like the finishing pass, but there is the option within the grooving cycle to set the finish mode to per side, and then you could set an offset for each side of the tool. I mean, I guess I would also ask the tooling experts, is that something that you see a lot of on that type of cutting where people are wanting to, set an offset for both sides of the tool, or is that really reserved more for dedicated finish passes?
It's more for finish passes where you have to control size. Other than that, that's really about the only time that I would do that. The inserts are pressed, and actually when you look at aerospace, a lot of the geometry we're using would be what we call an RO, which is ground. So the insert consistency and the size of that insert is really a fairly tight tolerance. So you shouldn't have a lot of issues even if you just use one offset.
Okay.
Yep.
So, Kevin, somebody was asking if they could see the tool definition for that Y-axis cutoff tool. I think it was just used, we were just creating just a regular grooving tool, and then we imported the holders that were given to us by Sandvik.
Yeah. Go ahead.
And I was going to say, those tool holders are on our website. You can download those models off the website, the Sandvik Coromant website.
Yeah, so here we have the actual tool block here, and the holder, the blade holder, is just an adaptive item. So here's that defines this all. So once you get that model from the Sandvik website, you can bring that in and define it as an adaptive item. And then this is just defined as a grooving insert. So we call it the cutoff Y-axis. The basis behind it is essentially, so I opened it up here. What we want to do is, so you just define it, and then you have to position it into the holder here and put the tool rotation that matches your Y angle to get it to fit into there. And it's based off of the tooling information that you would get from Sandvik that would give you that tool rotation. But then you can just use this tool shift to kind of get that into position.
Okay, so yeah, and just to clarify, I mean, that would be similar for all recent versions of ESPRIT and even some older versions as well. You would use the same tool type and just import the holders.
Just defined as a grooving insert here. So
Okay, so somebody else was asking about constant surface speed on the y-axis part off. As far as I know, it would just be, there really wouldn't be any difference from a regular cutoff operation, but maybe John has something to add to that.
Well, depending on the machine, some machines you'll have to turn on the feature to be able to switch the surface footage from the x-axis to the y-axis, so it's reading the y-axis for the surface footage. I know that Akuma's have added that feature to their machines, and then there's other machines out there. I'm not sure what the code is to do that. If you're unable to do that, you can make incremental steps in the program to change the surface footage manually as you come in towards center. And then keep in mind, as you get towards center anyways, you maximize your surface footage at some point. So you'd find possibly if you can't do one or the other, maybe you find a constant RPM that would give you what you need, and you can program it with constant RPM versus surface footage.
Okay. So there were a few of the attendees that were also asking how we created the features for the prime turning operation, and really there's several ways to do that. For that particular part, I had programmed a conventional roughing cycle and then smashed the toolpath and then modified the lead-in to match the recommendation from Sandvik. But you could also draw the toolpath. I mean, really the main point is, like Kevin mentioned, is that it may take a little bit longer to program, but if you have a high volume part type situation, spending that little bit of extra time and is going to be well worth it over the course of multiple parts. So that's kind of the main thing you want to keep in mind is, is the extra time worth what we're going to save at the machine? And if it is, then go ahead and spend it. And then the insert technology is going to be located on either the common machining toolbar or the turning tab, depending on which version of ESPRIT you're using. But the main thing is too, when you're going to have a separate contouring operation for each one of those passes, so you want to make sure to use the feature group so that you're able to control all those passes with one parent operation.
the smash function here is also underneath. So once you create your initial turning cycle and you want to smash or get the geometry from that, you can just go to edit toolpath here, select the actual toolpath that you want to smash. So for here, let's just say this is my turning cycle, and then it gives you the option right here to smash that and turn it into geometry.
Yeah,
and then you would want to change toolpath.
And then the smash function is just part of the accessories toolbar in 2020. So, but like I said, you could also draw it too, and and use the copy paste command to kind of speed up the process once you get one of the passes created. There's also a question about importing 3D tools. As you can see, that's certainly a possibility. Sandvik, I think John mentioned the tools for the y-axis cutoff are available on their website, but there's capability in all the recent versions of ESPRIT for importing those solid models. So I think we hit all of the more commonly asked questions that transpired throughout the session. Hopefully you found this session helpful, and like I said, you can check out our website ESPRITCAM.com/webinars for any additional information on upcoming webinars, as well as the ones that have been recorded already. So that part of our website's constantly being updated with new information. So be sure to check that out. And thank you again for joining.
Thanks, everyone.
Thank you.